We have come to the analysis session of our workshop. So in this we'll cut into three parts. So that is, one is analysis of cell, that is defining of hematopoietic stem cells. Second is defining of beads, and third one is a calculation of hematopoietic stem cells enumeration. So as per the ISHAGE guideline, we have to define stem cell, hematopoietic stem cells. They should be viable as 7AD negative. They are originating from the leukocytes, which is from CD45 positive, CD34 positive, clustered in a CD45 dim, as well as low side scatter, and they should fall in lymphoblastogenic region, and which is artifact free and excluded from apoptic cells, platelet clumps, and the RBC debris. So in the analysis of defining hematopoietic stem cells, we will use the sequential gating as per the ISHAGE. In this, we will define different plots. So we will actually make the plot so that sequence is, first plot will be the forward scatter and side scatter for the guidance. Second plot will be forward scatter and time plot to know the acquisition status. Third will be singlet plot, forward scatter area versus height. So we are going to eliminate the doublets. Third will be the viability, where we are defining the 7AD negative cells as a viable. Fourth will be the 45 versus side scatter to locate the CD45 WBC. Fifth will be the 34 versus side scatter to define CD34 cells as well as to remove the non-specific binding of CD34. Fifth will be forward scatter versus side scatter to define lymphoblastogenic region and CD34 cells. And finally, we will locate the beads and put singlet beads gate. Acquisition file has been transferred to the system, and this is third party software Kaluza, where we are going to analyze our CD34 enumeration. So first, before going for the analysis plot and template, we will have to check the compensation. So these are the all possible combinations where we are going to check the compensation for this, like this. So if the data is like uncompensated or overcompensated, you are going to miss your actual population of interest. So this is how the compensation will help you to analyze the data and minimize the error to generate the results. So I am going to check for all the plots where my compensation is fine. So I think it looks good. I may have to adjust for one or two places. So this is our bead population, you can see here. Okay, so we will check it for both the tubes here. So this was the first tube and this was the second tube. So I'm going to check it for second tube at all. So Kaluza has one more option. You can copy the first data set compensation to the second data set. So it will save your time. So compensation looks good. So we'll come to the actual analysis part, and we are going to start defining hematopoietic stem cell. So after the compensation of our data file, we will start the actual analysis, where we will see the each plot and the importance as per the ISHAGE guidelines. So our first plot will be to define acquisition rate or acquisition status. For that, we need to have the forward scatter area versus time plot. So looking at this, there is no error while acquisition, so we can go ahead. So go to the next plot. That is the definition of singlets. So we need to have, if we see area versus if we see height over here. So these are our singlets cells which has a similar height, and those cells which has a higher area, they are the doublet cells. So we will define this region, and I'm going to put one gate over here. So this is a gate. These are the singlets. These are the singlets. So next plot will be a defining viable cells. So we should have one more plot over here. So I'm going to take one plot. So on the y-axis, the side scatter. On x-axis, we should have the 7AD. So 7AD positive cells will be the non-viable dead cells, and negative will be the viable cells. So we are going to put a gate here. So this is a gate. So we have to label this is a viable cells over here. So till now we are defined the singlets and then viable cells. So we have to show the singlets over here. So out of the viable cells, so our next criteria to define WBC. So we need to have one more plot. So again, to define WBC, we should have the side scatter over here and 45 on the y-axis. So this is defined, and these are all from the viable cells. So you can see here, if I take a forward scatter here, you can see there are a lot of non-WBC cells. So we have to remove these cells and put a gate on the 45 WBC. So we, at our practice, we use the side scatter in logical scale to define the leukocytes. So we'll define these as CD45 leukocytes. So this is the gate. We have to define CD45 leukocytes. So we can make it this. So once we have defined this, so till now we have defined the singlet cells, then 7AD positive, negative, that is viable cells, and the CD45. So to fulfill next criteria, we should have one more plot to define the 34 positive cells. So for that, we need to have side scatter over here on the y-axis, and on the x-axis we should have the CD34. And from the CD45 leukocytes. So we have to define from the CD45 leukocytes. So we have get rid of non-viable cells over here, then we get rid of the non-WBCs, and we will get only CD34 population over here. These are CD34 positive cells. So we'll label as CD34 cells. And you can see over here there are non-specific binding to CD34 from the granular side. So we want to eliminate that. So as per the next definition, so till now what we have done, we have defined singlets, then viable cells, then from leukocytes and the CD34 positive cells. So next criteria to define CD45 versus side scatter. CD45 versus side scatter, and we will show the CD34 events over here. So this works as a guidance plot at all, so like CD45 and 34. So you can see if I minimize the gate, I'm going to lose the CD34 cells. So this is how you can make it out, where you should stop the gate, where you should do boundary of the gate to put the gate. So in this gate criteria, we are going to define the dim CD45. So how to check that dim CD45? So before that, we'll put one more gate over here from CD45 lymphocytes to define the CD45 positive lymphocytes which are bright. So we'll color this and we'll write CD45 lymphocyte over here. And now using this, we can make sure what is bright and what is dim. So if I say here lymphocyte, you can see a clear cut population which is 45 bright. And if I go to the lymphocyte over here, define the gates, the basis of lymphocyte positivity. So these are the cells. There are from CD34 gate. We'll check it again for the intensity with the lymphocyte population. You can see here. So again, we'll have to show CD34 events. This is as per the criteria. So we can call this as a dim CD45 and low side scatter. So till now we are defined hematopoietic stem cell as they are from singulates, they are viable, they are from leukocytes, CD34 positive, dim CD45 and low side scatter. Now we have to define the next step, that is a lymphoblastogenic region. For that we should have FSC versus SSC over here. In this plot will have to show only CD lymphocytes. Put the gate here and to eliminate the artifacts like RBCs and debris, etc. And we will rename as lymphoblast region. So this is a lymphoblast region. So we can see here we have getted the cluster lymphocytes and we have eliminated the junk. Even in this you can see over here in this plot we have eliminated the non-specific binding from the lympho region to the CD45. So to define HPCs we need to have duplicate of this plot and we will show CD45 dim and low side scatter cells over here. So you can see here these are our true CD34 positive hematopoietic stem cells. So we label CD34 positive hematopoietic stem cells and the number is gate is 115. So these are free from artifacts, so eliminated the debris, RBCs and clumps. So we have defined stem cell events, that is CD34 positive hematopoietic stem cells. The number is 115. Next step is to define bits for the calculation purpose. So for that we should have 45. So any channel, fluorescence channel, the bits are going to express, and from the ungated, please always keep in mind. So you have to have on ungated. So these are our bits. But in our practice, what we do, you can see here they can be gated from this channel, they can be gated or any channel. So You can look at this. So there are like, you can detect on any channel. So our practice we use on the APC, so which has a minimized interference of the cells, and you can easily get this bits over here. So we are label these as a bits. So these are bits we are defined, and I will try to color this with different color. So one more thing we are doing in our practice is we put the non bits region over here. You can see here all these are non bits. So reason being the putting the gate on the non bits to correct the viability percentage. So if you can see here, the viability is 98.87. So once I put the gate of this non bits on this singlet event, so viability is 99.76. So our viability was less just because of the number of bits. So that is a correction we have done. So next plot is to define singlet bits. So they should not be a doublet, so they should not be broken anywhere. So we need to have the fault scatter over here and time plot over here, and we'll have to show the bits only. So you can see here these are the bits. Either you can use linear fault scatter to define bits, or you can use logical scale to define it. So these are actual bits over here, you can see. So we'll put the gate on this, define our bits. So again we'll rename this as a singlet bits. And we'll find out the number of bits over here, which is, and in our practice we use gate basis on the force scatter, logical scale. So using ISHAGE guideline, what we have defined till now, we have defined CD34 positive stem cells on the basis of ISHAGE guideline. So what we have defined, the hematopoietic stem cells are from the singlets, they are viable, they are from the leukocytes CD34 positive, low CD45, a dim CD45 and low side scatter, and falling in lymphoblastogenic region. So we have got our bead number as well as the CD34 positive stem cell number. Using this we are going to calculate it. So apart from that we use guidance plot. So that is one guidance plot is 45 versus 34. So this is the guidance plot. These are our bits and these are the CD34 units. To know we are not eliminated or not missed out any events for our calculation. So using this bid number and CD34 events, we will calculate the absolute count of hematopoietic stem cells. So we'll go to the calculation part. For the calculation of hematopoietic stem cell and for the single platform assay, the formula is absolute CD34 positive HPC count is equal to number of CD34 events getted divided by number of beads collected into bead concentration divided by sample volume and into dilution factor. So for dilution factor, we dilute the sample in case where the post PBSC harvest sample in which the count is more than 40,000. So for it recommendation, the kit is suitable up to the count less than 40,000 for BD and less than 30,000 for Beckman Coulter. So we'll do dilution only if the count is more than 40,000, either it's pre-PBSC or post-PBSC sample. So we'll see the example actually what happened in this formula. So in our assay, what we have seen, the number of CD34 events were 1158. We BD count the 5000, and as per the BD kit, true count tubes have number of beads are 48,600. Sample volume was 100, and dilution factor was only 1 because we have not diluted the sample in this. So if you do the exact calculation, the absolute CD34 stem cells are 112.55 per microliter. Now we'll see, though the formula looks complex and many of the people get confused, so we'll make it's very easy. So we'll divide it into two. What we have to find out? So with the beads, we'll find out the number of volume of sample, how much sample or what was the quantity acquired for the particular assay, and then we'll find out the number of CD34 for the per microliter. So I have divided this formula into two. What you have to do, number of beads we have acquired is 5000, and this beads concentration per microliter is 486. How is this? Because for 100 microliter is 486.00, so for 1 microliter it's 486 number of beads. So derived sample volume is 5000 beads collected divided by concentration per microliter, that would be the 10.288 microliter. So our sample whatever we are utilized to calculate this or assay or recorded is 10.288. So number of CD34 events were collected is 1158 for 10.288. So for per microliter, this number of bits divided by sample volume is equal to absolute CD34 count per microliter, that is 112.55. It actually makes this. So analysis has been done for both the tubes which were acquired in the duplicates, and the report has been generated. This is how the report generates in a Kaluza software. In our setup, so both the tubes, this is the report for absolute count for the first tube, this is for the second tube, and average is 112.52. And we type this report and then upload on the EMR system. So this is the Excel sheet report where we actually type the report from the Kaluza report form, and we put the value along with the patient detail demographics here, then viability, MNC. Again we type because to minimize the typological error and counter checking. So we put the number here, 34 number here. We generate stem cell percentage from the report generated, absolute count, and then sample receiving time, reporting time. And after taking the printout, we'll sign this and send it for the typing, and after typing the report will upload on the EMR. So meanwhile, we'll go for the delta check. So we maintain the delta check for each and every patient, and stem cell control done on for that day. So with this we'll end the session, and we'll take a questions from the participants. On behalf of Hematopathology Laboratory, I would like to thank all the participants and the TCS for arranging and organizing this one for us.